Hello everybody and welcome to AlgoExpert. In this video, we'll be covering the question of A-star algorithm. Now, A-star algorithm is a path-finding algorithm that is used to find the shortest path between a start node and an end node. So before we dive in and talk about how this algorithm works, let's discuss the problem that we're being asked so we make sure we know how to solve it properly. So for this question, we are going to be given 5 inputs. We're going to be given a start row, which we can see here, a start column, an end row, and an end column, as well as a graph. Now the graph is going to come in as a multi-dimensional array, so we're going to have an array of arrays, and each of the elements in our arrays are either going to be a 0 or a 1, where a 0 represents an empty space, so something like these empty spaces here, and a 1 represents an obstacle, otherwise known as a block that we cannot move through. So our goal for this question is to look at the start position and the end position and find the shortest path between them. Now we're going to return that shortest path in an array. We're going to start with our start node, end with our end node, and then have the order in which we visit all of the different positions in the shortest path. So all of these subarrays right here, or the arrays inside of the arrays, are simply going to contain 2 elements. The first element will represent the row of a position that we've moved into, and then a column of another position that we moved into. All of these positions here are going to be in the shortest path, and of course we should return this in the correct order, again including the start node first and the end node at the end. Now in the situation where there is no shortest path, we simply need to return an empty array, so something that looks like that, and that is pretty much the problem statement and what we're being asked to do. Now there is a few more things that we want to consider before we start solving this problem, and those just have to do with the validity of our input or any particular edge cases that we might run into. So having a look here, we can see we're having 5 inputs. So this graph, which is obviously not going to come in looking like this, but I've kind of drawn it out. And then the start row, start column, end row, and end column. Now the first question I would want to ask my interviewer, or that I might come up with, is can we assume that the start row and the start column, or I guess the starting position, is valid? In other words, is the position that we're given guaranteed to be in the graph that we are given as well? Now, an example of when that might not happen is if, say, we were given a start row of 7 and a start column of 3. This position here is actually not in this graph on the left-hand side of my screen, and well, we're not going to be able to actually find a path because, well, the start position is not valid. Now for this question, we know that we're going to be given a valid start position because that's stated in the question prompt. But again, that's something you're going to want to ask your interviewer and making sure you're clarifying before you go ahead and get started. Now, obviously the same thing with our end position. We want to make sure that that is valid. And we also have a few more questions that we might want to ask relating to these positions. Another question we might want to ask is, can the start position and end position be on the same block? So can I technically have my start and my end on the same position? Now for this question, that's not going to happen. That's stated in the question prompt, but again, something that you want to ask your interviewer. And another question that I can think of off of the top of my head is, will the start position or end position ever be on an obstacle? So will I ever have the situation where my start position is actually where there is an obstacle in the graph? So all of these questions are things that you would want to ask your interviewer and make sure you clarify before you get started. And oftentimes these will actually save you a significant amount of work, because if you can be guaranteed that these edge cases won't occur, well, then you don't need to check for them and it makes your algorithm that much easier. So now let's just quickly have a look at this graph and our sample input, which is on the right-hand side of our screen here, and see how we actually came up with this for this input. So if we have a look, this is our start position right here, and this is our end position. And having a quick glance at the graph, we can see that the shortest path is not going to be something like this, but it is going to be something like this. So this is what our shortest path will look like. Now we can quickly go through and just compare the positions in our output to the kind of line, or I guess path, that I just drew out. So we have 0, 0, which is right here, which is the second position. Obviously the start position is 0, 1 over there. We also have 1, 0, which is right there, so that covers that. Then 2, 0. And then 2, 1 right there, then 3, 1, and then 4, 1, then 4, 2, and finally we end with the end position of 4, 3. So that is how we came up with that, and that is what we are looking for from a given graph. We want to have all of the different positions contained in the shortest path in the order in which they were visited. So now that we understand the problem, let's go ahead and talk about the A-star path-finding algorithm and discuss how we can implement that and how that works. Now, the A-star algorithm is what's known as an informed search algorithm. Pretty much what that means is we use something called a heuristic to try to determine which nodes we should visit next. Now, a heuristic is pretty much just an educated guess that we try to make about how far away a certain node or a certain position is from the end node. So every time we decide which node we're going to be visiting next, we're going to consider two main things. How long or how much distance has it taken us to get to the current position, and how long do we think or how long is our guess that it's going to take to get to the end position. Now, there's many different type of heuristic formulas, and the type of heuristic that you use is really going to determine how efficient your algorithm is. Now, the reason for that is that if you have a bad heuristic, you're going to be considering a lot of nodes that you don't actually need to look at, or that will probably be bringing you on a longer path than is necessary to get to the end node. So the goal of A* is to visit as few nodes as possible and to find the shortest path to the end node without visiting most of the nodes in the graph. Now, of course, we have obstacles in our graph, and it makes it pretty much impossible to have a perfect heuristic. If you were able to have, say, a perfect heuristic where you could actually perfectly estimate the distance from one node to the end node, then you would always find the shortest path by only ever considering the nodes in the shortest path. So the idea behind the heuristic is to give us a really good educated guess as to which nodes we should look at next that are currently on the path that we have found. Now, this will all start to make sense as we discuss the algorithm, but just understand that a heuristic is a guess, and the better guess that we can make, the better our algorithm is going to perform. So for this specific problem, from any given node or position in our graph, we can only move in 4 directions. So up, left, right, and down. We are actually not able to move on the diagonals. That is not allowed for this specific problem. And just note that if you were able to move on the diagonals, then this algorithm would be slightly more complicated, because to move diagonally between 2 squares is the distance of root 2, whereas to go either to the right, up, down, or left only costs us or is a distance of 1. So just keep that in mind. And again, if you were given a graph problem and you wanted to use something like A*'s algorithm, make sure you're clarifying that with your interviewer and asking them what directions you are able to move in. Again, for this problem, we can only move in 4 directions: left, up, right, and down. So now that we understand that, we can dive into the A* algorithm. Now, in A*'s algorithm, we decide which nodes we're going to be looking at or visiting next based on 3 factors. And those 3 factors are scores or costs associated with every single node. And they're denoted by H, G, and F. Now, H stands for our heuristic value. So pretty much the guess from how far our node, whatever has this H score, is to the end node. The next is G, and this is the current shortest distance from the start node to this given node. And F is simply the addition of G plus H. Now, when we look at what node we want to visit next, we will look for the node that has the current smallest F score. The reason for that is based on our guess and based on the distance that we found to get to this node so far. It is the shortest distance, and we are hoping that it's going to be on our shortest path. So we're going to be kind of plucking nodes out of an open set, or of whatever we want to call it, of some kind of priority queue that have the lowest F score. So keep that in mind, but I will go through the algorithm and all of this will start to make sense. So we're going to start with our start node, and the start node always has a G score of 0. So what I'm going to do to make this really clear as we explain this algorithm is I'm going to write the G score, the H score, and the F score in this orientation in each of my positions or each of my nodes. This way, we can really clearly see what all of the different scores are, and then we can pick the node that has the smallest F score to look at next. So the way this algorithm will start is we will look at our starting node, which is right here, and we will consider all of its neighbors. So we'll look to the left, to the right, up, and down. Now, of course, if any of the neighbors are invalid, say like going up or going into the obstacle, which would be down, we're not going to look at them. We're not going to bother doing a score for them because there's no reason to do that. We cannot move into those positions. So looking at the start node here, the only 2 neighbors that we need to consider are left and right. So let's actually start by giving a G, H, and F score to our starting node. And this is what we do when we start our algorithm. We start by giving this score to the starting node, and then from there, we branch out, look at all of the neighbors of the starting node, continue to score those nodes, and then look at the next node that has the smallest F score. And so on and so forth, we continue that process until we find this ending node and we found the shortest path. But anyways, what is the g-score of our start node? Well, the g-score, remember, represents the distance to get from the start node to this node. Well, obviously, this is going to be 0 because the distance from the start node to the start node is 0. Now, the h-score. What is the h-score? Well, the h-score is our heuristic score. So now we need to talk about what heuristic we're going to use for this problem. Now, you technically can pick whatever heuristic you would like, but there is some that make more sense based on the type of problem that you're given. Now, in our situation, we can only move in 4 directions. So we can only move up, left, down, and right. Now, this calls for us to use a heuristic, which is known as the Manhattan distance. Now, the way I like to think about the Manhattan distance is like an L distance. So pretty much this would be the Manhattan distance from the start node to the end node. We just take the differences between the rows and the differences between the columns of our start and end node, or of whatever the node is that we're at in our end node, and add those together. So in this situation, our end node has a position of 4, 3, and our start node has a position of 0, 1. So all we do is we take 4 and we subtract it by 0, so 4 minus 0, and we add that to 3 minus 1. And what do we get? Well, we get a distance of 6. And if we have a look, 1, 2, 3, 4, 5, 6 is the distance that it takes if we just look at the L to get from the start node to the end node. Now, if we're looking at another block or another position, just to show you another example, we can see that if we were trying to calculate the heuristic, say, of this block right here, even though it is an obstacle, but imagine it wasn't, then the distance would simply be 2, because we would look at this node right here and then this node. You can try the math for yourself if you'd like to prove it, but pretty much we're looking at 3, 2 as the position, and we're looking at 4, 3 as the other position, so that would be 1 plus 1 if we do those subtractions and then those additions, and well, that gives us a distance of 2. So again, just trying to estimate using this Manhattan distance, how long it would take us, or the distance it would take us to get from any node to the end node. Now, there's other type of heuristic distance formulas that we could use, but for now, we're going to stick with Manhattan distance, and that's typically the one you use when you can only move in 4 directions. Now, if we were able to take diagonals, then we may want to consider what's known as Euclidean distance, where we simply just take the distance of the diagonal between the 2 points. So that would be a slightly more complicated distance formula, but still pretty straightforward, and you can figure this out by just looking at, say, a right-angled triangle and doing the calculation of the length of what you would call the hypotenuse of that triangle. So anyways, that is the heuristic that we're going to use. So if we have a look here, we saw that the calculation of that heuristic gave us a value 6. So we have 6 in the top there, and then the total f-score, it's going to be kind of messy because I have stuff on here, would be a 6. Now, since we have not considered any other nodes to start, we're going to look for the node that has the shortest f-score, which will always be the start node when we start our algorithm. So we're going to pluck out our start node. We're going to mark this node as visited. Now, the way that I'm going to mark this node is just by drawing a little triangle in the corner just to show us that, hey, we have looked at this node and we don't need to look at it anymore. And then we're going to consider its neighbors. So the 2 neighbors are to the right and to the left. So now we're going to figure out what their G, H, and F score is. So looking to the right to start, we see that we have a g-score of 1. The reason our g-score is going to be 1 is because the previous g-score was 0, and since we can only move up, down, left, or right, to move to any position is simply an addition of 1 from the original g-score. So we just look at whatever the last g-score was, so whatever the position is we're currently looking at, and add 1 to it whenever we move into a new position. So the g-score of this is going to be 1, and the h-score of this is going to be 5. Now we can figure that out pretty easily by just drawing the line here. 1, 2, 3, 4, 5. That is the estimate from the Manhattan distance, and we'll calculate the h-score every time we reach a new node. Now, looking at the f-score, we have a score of 6. So now we've looked at that one, or we've calculated the scores for that node. Now let's look to the left and let's calculate this one. So we know our g-score is going to be 1, and we know that our h-score actually is going to be 7. Now, the reason for that is that the Manhattan distance between the block at 0, 0 and the block at 4, 3 is 7, so we can write in the heuristic value of 7. Now, what is our total f-score? Well, that is going to be 8. And now we have fully visited this node. We've considered both of its neighbors and given them a score, and we will have added those neighbors to what we're going to refer to as the open set, or some data structure that will then pull these nodes from as we continue with the next step. So now we're going to repeat the process that we just did, but we're going to do it on the node that has the smallest f-score. So having a look here, we've already looked at the start node, so we're not going to look at that one again. But now we have this one here that has 8 and this one here that has 6. So obviously 6 is smaller than 8. So we are going to consider this node. So let's go ahead and mark this one as visited because we've considered it. And now what we'll do is consider its neighbors. So we'll look to the left and we'll look to the right. Now we can start with looking to the left. And when we look to the left, we can see that if we try to figure out what the G-score of this node on the left is going to be, well, that is going to be 2, right? Because we'll have 1 here, and then we'll add 1 to move left. I know this doesn't really make sense, but let's say we're just performing the algorithm and going through the steps. We would calculate that this node, the start node here, would have a G-score of 2. So since that G-score is greater than the current G-score that we have, we are not going to actually consider this node, or we're not going to update its score. Again, because there's no point in updating that score, we already found a shorter distance to get there, so we're not going to take the longer path to get back to the start node. But now we can have a look at the right neighbor, and we can see that, oh, hey, it doesn't have a G-score, or it doesn't have an H-score, so we can go ahead and we can calculate that. So what do we say the G-score is? Well, the G-score is going to be 2. We simply add 1 to 1. And then what is the H-score going to be? Well, this is actually going to be 4 because technically from here, we would just go straight down. So looking at our F-score, that's going to give us a total F-score of 6. So now we visited the start node and the neighbor to the right, and we'll repeat the process. And now we're going to visit this node because it has the shortest F-score, shorter than 8. So what do? We repeat the process and we say, okay, can we go to the left? Well, that's not going to make any sense to do because the score of 2 plus 1 is 3, which is obviously greater than the current score here, which is 3. So we're not going to move to the left, or we're not going to update the G-score, H-score, F-score of that node, but we will go to the right because we see that this does not yet have a score. So we go here and we say the G-score is 3, and now we calculate the H-score. What is the H-score? Well, that is going to be 5. So now we have 3 plus 5, and we get a distance of 8. So now we can go ahead and mark this node as visited. We've considered all of its neighbors, and we'll repeat the process again, but now looking at the 2 nodes that have currently not been visited and that have an F score. So we have the F score of 8 and we have another F score of 8. So which one do we pick? Well, in reality, it doesn't really matter which one that we pick. Some people will say, let's pick the one that has the smallest G-score. That is a valid comparison if you want to do that, and that does make sense to do. But again, doesn't really matter which one you pick if they have the same F score. So let's, just for the sake of it, pick this one that has the lower G-score of 1, and let's consider this. So I'll just preemptively mark it as visited, although technically you can mark it as visited after. It doesn't really matter the order in which you do that. And now let's look down and let's look to the right. Obviously, it doesn't make sense to go to the right. I've already covered why we wouldn't do that. So let's just go down. So now the G-score is going to be 2 and the H-score is going to be 6. And that gives us a total score of 8. So now we visited the top 4, we repeat the same process, and again, we pick the node with the shortest F score, or the lowest F score. So again, we have a tie, 2 8s, doesn't really matter which one we pick. I'm going to stay consistent and pick this one because it has a lower G score. So now we go ahead and we get a G score of 3, and we get a heuristic value of 5. And now, what do we have? Well, we have the same F score of 8. So we can go ahead and mark this node here as visited and repeat the process. Now, since we have 2 with the same score and they have the same G-score, well, we can kind of just randomly pick which one we want to do. So I'm going to pick this one up here. So now I have a distance of 4. I have a heuristic value of 4, and I get a value of 8 as my F score. So now we mark this one as visited, we have seen it, and we repeat the process. So now we're going to pick this node over here to visit next. We're going to look down. Obviously, we can't go there because there's an obstacle. We're going to look right, and we're going to calculate the score to the right. So looking to the right, we get a G-score of 4, we get a heuristic score of 4, and we get a value of 8. We go ahead and we mark this node as visited, and now we repeat. Again, we have a tie, so I'll just do the one on the right-hand side just to show you how that will work. So now we get a value of 5, we get a heuristic value of 3, and we get a total score of 8. So now I'll mark this one as visited, and we'll go ahead and consider this one. So hopefully you're getting the idea of how this works. I'll start going a little bit faster. So now we can go to the right, and we can go down. We'll start by looking to the right. If we look to the right, we get a value of 5, we get a heuristic value of 3, and we get a total F score of 8. If we look down, we get a G score of 5, we get an H score of 3, and we get a total F score of 8. Then we can mark this one as visited. We've already seen it. And now we have 3 nodes or 3 positions that actually are all tied. So we have to pick which one we want to consider. So let's actually go ahead and consider this one over here. Again, we'll just randomly pick this. So now we get a G score of 6. We get an H score of 2, and we get an F score of 8. We can go ahead and mark this one as visited and repeat the process. Now, this G score here is obviously greater than these 2 G scores, so we'll pick one with the lower G score. We'll pick this one to look at. So here we have to look to the right and we have to look to the left. And now what we actually do, since we've already found a score for this node and we've already found a score for this node, is we have to make sure that if we're going to update these values, we have a lower G score to update it with, right? So if I'm looking to the right here, the G score that I would be updating here would be 5 plus 1, which would give me a value of 6. So since these will have the same G score, there's no reason for me to actually update this node and potentially change its F score, right? I would only ever be lowering the total F score if I was changing this G score to be a value that is lower than it's currently at. So there's no reason for me to update this, so I can simply skip the right neighbor. Now, same thing with going to the left. I have a neighbor here that has a G score of 4, so there's no reason for me to update the G score to be 6 because, well, that's going to be greater than 4. So we just go ahead and mark this one as visited because we've now seen it. And now we have no option but to select this one. Well, we do, but this one has a higher G score, so we're not going to look at that. So we go ahead and we have a look at this one, and here we can go up and we can go down. We could go to the right or left, but since there's obstacles there, we're obviously not going to consider that. And what do? Well, we look up to the top. Obviously, we're not going to update that because, again, the G score is lower than what it would be updated to. So we simply move down and do the calculation. So we get 6, we get 2, and then we get a total F score of 8. Now we have 2 F scores that are tied. So let's actually, first of all, mark this one as visited, and we can consider either this one or this one. We know that if we have a look at this one, there's really no point. We're not going to be updating either the left or right neighbor. So we'll just say that, hey, we had a look at this one, we'll mark it as visited, and now we'll have a look at this node right here. So from here, what will we do? Well, we will look to the left, we'll look up, and we will look to the right. And we will see that obviously there's no point in going up because we're not going to be making an update there, but we will go to the left. So when we go to the left, we'll get a score of 7, and we'll actually get a heuristic value that is now greater than what this one was of 3. So now we'll have a total F score of 10 for that node, and then we'll look to the right and we'll do our update here. So now we have a G score of 7, we have an H score of 1, and then we get our total F score of 8. Now we can mark this node as visited because we've already looked at it, and we have 2 nodes that we can consider, this one right here or this one here. Obviously, we pick the one with the lower F score, which is going to be this one here, and then we go ahead and we check its neighbors. We say we can go to the left or we can go to the right. We go to the right because there's no point in going to the left. And now we see that we hit the end node. So as soon as we hit the end node, we can actually stop the algorithm because we are guaranteed to have found the shortest path. And if we want to find the distance of the shortest path in terms of how many cubes or positions we actually had to visit, then we can just look at the F score of the end node. So we can score it and we can say its G score is 8, its H score is 0, and then its total F score will be 8, which is obviously what most of the predictions from a lot of these blocks were. So that is pretty much the A* algorithm. Now, some of you may be thinking to yourself, okay, that's great, I understand that, but how did you come up with this right list here? How do I actually get the positions of the nodes that are in the shortest path? Because what I just showed you did not keep track of the shortest path. It simply figured out the distance or the shortest distance to get from this start node to this end node right here. Now, of course, this distance is correct. Now, you might notice that there's actually 9 elements in here. The reason why there's 9 is because we do always include the start node and the end node, so we're always going to get one more element than what the actual distance of the shortest path would be. But if we want to keep track of what the actual path is, then we just need to make a very slight modification to this algorithm. So this is fine, this tells us the distances, but we want to know what the actual path is. Now, the way we do that is pretty straightforward, but at every single node, whenever we do these scores and we check this out here, we actually also store what node we came from. So what node did we come from that forced us to update our G-score? So whenever we update the G-score of a node, or we add the G-score, assuming it doesn't have a G-score already, then we also update on this node which node we came from. So let's just repeat this process. I'm not going to erase what I have on the graph here, but I will just simply go through and show you how we would actually keep track of what node we came from. So if we're looking at the start node here, we go left and we go right. So here, since we would have forced an update of the G-score by moving to the left and to the right of 1, we simply can put an arrow from this node and from this node saying, hey, we came from the start node. Now, if we go here and we're looking to the right, same thing, okay? This forced us an update, so we'll put an arrow like that. Same thing here. This one would have came from there, so we put an arrow like that. Now here, this came from there, so we put an arrow like that. Same thing here, came from there, so we put an arrow like that. So hopefully you get the idea, but it's kind of constructing a path. If I'm on this node and I want to figure out how I got to it, all I do is I just track back and I look at all of the nodes and what node they came from until eventually I hit the start node. But continuing, we can do the rest of the arrows. So from this node, we would have came from here. From this node, we would have came from here. From this node, we came from there. From this node, we would have came from there. I'm just doing the obvious ones first, and then I'll actually do these two, which might be a little bit more complicated. From this node, we came here. From this node, we came from here. And then, of course, from the end node, we came from here. So from the end node, if we want to figure out the path that we used to get here, all we do is we look at the node that we came from. So we say, okay, that's this node. We add that node to the path. Then from this node, we say, okay, did we come from a node? Yes, we did. We came from here. And then from this node, we say, what did we come from? And we continue along the path, adding these positions to our array as we go until eventually we get to the start node and we'll realize that this node didn't come from anywhere. So as soon as we get to a node that didn't come from somewhere, we know that that must be the start node because the start node, well, started on itself. And then that tells us what the actual path was that we took to get to this node. Now, the reason I paused or I didn't show you these two nodes is because I just wanted to show you an example of how we might update the node that we came from, just to show you how that works in case we have to do that. But if we have a look here, this node would have originally, when it was first updated, came from here. And then this node, when it was first updated, would have came from here. So notice these obviously are not facing each other, but in the situation where going from this node to this node updated in a shorter G-score, what we would have done is we would have changed this arrow here. So we would have changed it to actually point to this node because that is the node that most recently updated this node's G-score and, well, in turn changed its F-score. So we need to change which node it came from. So that is a possibility. And whenever we do an overriding update, we will change the node that this node came from. So just change kind of the pointer there, and then that will make sure that the path is staying valid. So this is obviously a pretty simple example. This is a small graph. There's only really two paths that we can take to actually get to the end node. But in graphs that are much larger, you can imagine that this algorithm will take a little bit longer to run, obviously, and will be more complicated. There will be more updates happening on a lot of these nodes, and there will be multiple different ways to get to the end node or to get to intermediate nodes. So there will be a lot of updates that are happening, and you just have to remember that you only update a node in the situation where the previous G-score plus 1 for this specific example is going to be less than the G-score currently stored on that node. So we can actually initialize all of the G-scores of all of the nodes in our graph as infinity to start. So that way, whenever we find any G-score that's actually equal to something less than infinity, we'll make that update. And then to update again, well, we would need to find a G-score less than whatever that updated G-score was. And if that happens, we would change the node that we came from. Now, before we look at some implementation details, it's worth noting how the A-star algorithm differs from an algorithm like Dijkstra's. If we were to visualize these two algorithms, we would see that Dijkstra's algorithm will expand its search in a flower-like pattern where it will kind of expand equally in all of the available directions. Now, if we have a look at A-star's algorithm, it will appear more like a line or like an arrow where it's expanding directly towards the end node. This is due to the bias, otherwise known as the heuristic, that we talked about previously. This additional value biases the algorithm and makes it favor going in a direction that is closer in terms of our heuristic formula to the end node. Now, this typically makes A-star's algorithm run much faster than Dijkstra's algorithm because it's generally already going in the correct direction towards the end node, whereas in Dijkstra's, it will expand evenly in all of the different available directions. Anyways, that was the core of the explanation, but now let's discuss how we can take this algorithm and actually translate it into code. So I've cleared the screen and I'm just going to write some really basic pseudocode to give you an idea of how we're going to start this algorithm. And then what I'll do is discuss the time and space complexity of it. So the first important question you should be asking yourself right now is, how am I going to determine which node to look at next? So obviously we know we have that G, H, and F score, and we're looking at this F score of all of the nodes that we're about to visit or that are in what we're going to call the open set, and I'll discuss that in a second, and we want to pick the one that has the smallest F score. So this, if we just used, say, an array, and we just looped through all of the different nodes and tried to look for the one with the shortest F score, well, that would take us O of n time, where n is equal to W times H, or the number of nodes. So if we're given a graph, right, and we're given a two-dimensional array where height is the height of the graph or the amount of rows, and W is the width of the graph or the amount of columns, well, then W times H tells us how many nodes we have. Well, we have to look at every single node, at least that is in our open set, and we could potentially have all of the nodes in our open set, or almost all of them, to figure out which one has the smallest F score. So that is probably not what we want, because we're going to have to look through every single node, perform the algorithm that I just talked about, and then we're also, on top of that, going to have to, every time we do that, find the node that has the shortest F score, or the smallest F score. So what is a better data structure that we could use to figure out which node to look at next? So the data structure that we should be considering using is actually a priority queue, and that would be implemented using a min heap. So you could call it a min heap, you could call it a priority queue. Doesn't really make a difference, but ideally we just want to be able to retrieve the minimum element in the queue or in the set or whatever it is that we have in a shorter time complexity or in a better time complexity than linear time. Now, if we're looking at a priority queue or a min heap, remember that to retrieve the smallest element from this heap is going to take us log n time, or O of log n time. So that is because we need to restore the heap property and rebuild the heap and figure out the next minimum element after we remove that element from the heap. So let's write some pseudocode now, and you'll hopefully start to understand how we use the min heap and how we actually kind of start with this implementation. So the first thing that I want to do is I want to actually initialize a heap that has my start node in it, because we want to start with our start node that has the lowest G score and, well, will have the lowest F score as well, at least when we're starting. So to start, we're going to initialize a min heap. So I'll say min heap, and then we'll be equal to, we can just say something like new min heap, like that. And then we would pass it our start node as the first value that we want to add into the heap. Now, just to make it clear here, if you were in a coding interview, you would not be expected to implement a min heap. You can simply say, hey, I'm going to assume I have access to a min heap. This is the interface for the min heap. So I want to have, say, an insert method. I want to have a pop method. I want to have an isEmpty method, so on and so forth. You can define all of the methods that you want to have for your min heap. And you're going to say, I assume I have access to this. I'm going to use the standard library, whatever it may be. And that is totally fine, totally sufficient. So just know that you will not be expected to actually create a min heap. You can simply assume you have access to one. And it's usually a good idea to define an interface for it and say, these are the methods that it will have on it and that I will be using. But anyways, we're going to start by initializing this min heap. So we have our min heap, and then the next thing we're going to do is we're actually going to get into a while loop, and we're going to say, while the min heap actually is not empty. So while min heap is not empty. So now that we have the start of this while loop, what we're going to do is remove the element that has the smallest F score from our min heap. And we'll assume that our min heap is going to sort or keep track of the elements from their F score. So we'll say that the node that we want to consider is equal to the min heap, and then the method we'll use would be something like pop or remove. Whatever you want to call it, I'm just going to call it pop, but we'll remove the minimum element from the min heap. Next, what we'll do is we'll say, okay, if this node is equal to the end node, So I guess we can just write end from there. So if node equals end, then we need to stop our algorithm. So I will say break. And then outside of the while loop, so at the very end, we would look at our end node and then retrace all of the steps and kind of reconstruct that path and return that. Remember, we'll do that because we'll have all of these different boxes that will have their arrows going to where they came from. So at the end node, we'll just kind of trace back and then we'll write down all those positions or put them in an array. Now, if it is not equal to the end, what we need to do is look through all of the neighbors of that node. So we're going to say for neighbor in, and then we'll just say node dot neighbors. Of course, this is not exactly what the algorithm is going to look like, but just some rough pseudocode so we get an idea. So for neighbor in node.neighbors. So then what we will do inside of here is we'll first check to make sure the node is not an obstacle. So we'll say if obstacle, and then we will simply continue. We can just skip that node. So we'll say continue like that. And then if it is not an obstacle, what we will do is we will check and see if we should update the F, G, and H score. So I'll simply write here, update F, G, and H score like that. And then the last thing we do here is we will insert this neighbor into our min heap with its updated F score. Now, if for some reason the neighbor that we're looking at is already inside of this min heap, all we need to do is simply update its F score or update its position in the heap, and then we can continue. The reason for that is if we change the neighbor's F score, we need to make sure that the heap is aware of that change. So we'll make an update or force an update in the heap to move that element around so it's in the correct position. So all we'll say here, just to hopefully make this clear, is insert / update heap. Again, I'm being really brief here. I just want to give you an idea of how this works. So that is the basic process. We do that. We run through this algorithm right here, and then as soon as we break, so as soon as we find the end, or as soon as the heap is empty, and if that is the case, that means we would have looked at all of the nodes and we're not able to find the end node at all, so pretty much there was no path to the end node, then we will go to the end of our algorithm, we'll figure out what the path was, or if there was no path, and we will return that. And that is how the A* algorithm works. Now, before we dive into the code walkthrough, let's quickly analyze this algorithm for its space and time complexity. And we'll actually start with the space complexity because it will make the time complexity easier to understand. So having a look here, the only thing in our algorithm that's actually going to use any auxiliary space is this min heap right here. And this min heap will only ever store at most the number of nodes that we have in our graph, assuming that, say, every single node was inside of the min heap, which we know will likely not happen. But anyways, that tells us that we'll have ON for space, otherwise known as O of W times H, because we know that W times H will be equal to N, where N is the number of nodes or number of positions in our graph. So our space complexity is big O of W times H. Now we have to look at our time complexity. So let's just start going through the operations that we know how long they take to run, and then we'll just add them together and figure out what the actual complexity is. So in our min heap, we know that we will only ever at most have W times H nodes or W times H positions, whatever you want to call them, will only at most ever have that. So having a look at our while loop here, we can determine that this will at most take W times H time to run. Next, we have a look here at our minheap.pop operation. So this operation right here, we know is going to take log of N, or we can write log of W times H. So W times H, and then we have log of W times H. Obviously, this here is a constant time operation. This for loop will be constant because we only need to loop through at most 4 neighbors. Now, inside of this for loop, we insert or update a value in our heap, and we only do that sometimes, but we will potentially do that. So this operation will take, again, log of W times H time. So if we have a look at this, these are the only operations inside of our main while loop that are actually going to take anything more than constant time. So we can simply add them up and perform the multiplication. And after doing that, we get that our time complexity is actually going to be O of W times H times a log of W times H. So that is going to be our total time complexity, and then our total space complexity is again big O of W times H. So now that we understand the space and time complexity of our algorithm, let's go ahead and get into the code walkthrough. So I'm here in my code editor and I have my A* algorithm function defined that takes in a start row, start column, end row, end column, and a graph. Now to get started, I'm actually going to define a class. This class is going to be called node, and this node is going to be used to store all of the information that we need about each of the positions in our graph. So namely the F-score and the G-score, as well as the node that we came from, and a few other things as well. So I'm going to define the initialization method. I'm going to say define init. This is going to take a row, column, and a value. Now, a reminder that the value is actually going to store the value of the position in the graph. So whether that's a 0 or a 1, so that we know if this node is an obstacle or not. Now I'm going to say self.id is equal to the string row plus a hyphen and then plus the string column. We're going to use this ID field later, and I'll talk about why we have it when we get to that point. But moving on, we're going to say self.row equals row. We're going to say self.column equals column. We're going to say self.value equals value. And then we're going to define, first of all, our G-score, then our F-score, and then the came from node. So the node that we came from to get these updated values. So we're going to say self.distance from start. This is going to be equal to our G-score. I'm just giving it a nicer name. I'm going to say that's equal to, by default, float infinity. Now I'll just put the comment here for G, just so we remember that this is indeed the G-score. Next, I'm going to say self.estimated distance to end, and this is pretty much going to be equal to the distance from start plus the heuristic value. So this is what we're going to call our F-score. Again, just to give it a nicer name, I'm going to call it estimated distance to end. This is our current guess for how long it's going to take us to get to the end node. And by default, this is going to be infinity, because if we have not yet visited this node, then we don't actually know, because we have no G-score. So really, G-score plus whatever the heuristic was will give us a value of infinity. Anyways, this will be our F-score. And then last, we'll say self.camefrom, and this will be equal to none, because by default, we've not yet been visited, so we don't have a node that we came from yet. Now, we actually need to create a node object for each of the positions or values in our graph, otherwise known as the two-dimensional array. So the first thing I'm going to do is say nodes equals, and then initialize nodes like that, and we're going to send in the graph. Now this is going to be a function. We've not yet defined it, but I'll simply copy this name and we will define it down below. So we'll move down and we'll say define initialize nodes. This will take in a graph, and inside of here, we are aiming to recreate this graph, except rather than storing ones and zeros, we want to store node objects that represent all of the ones and zeros that are inside of our graph. So we're going to go ahead and say nodes equals an empty list, and then we're going to do a for I, comma, row. In enumerate, we're going to enumerate over graph. We're going to start by appending an empty row or an empty list or array, whatever you want to call it, into our nodes array. So nodes.append, and then we're going to say for j, comma value in enumerate, and we're actually going to enumerate not over the graph, but we're going to enumerate over the row like that. And then we will say nodes I dot append, and we'll create a new node object with I, j, and value, where I obviously will represent our row, j will represent our column, and value will represent either a 0 or 1 based on what was stored in the current index or in the current position in this graph. Now, once that's done, we can return nodes, and we will have a two-dimensional array of all of our nodes that is in the exact same structure as our original graph, except instead of having zeros and ones, it will have node objects inside of it. And now we just need to do a little bit more initialization. So we'll start by defining our start node. So we're going to say the start node is equal to nodes, and that's going to be at index start row and start column. Then we need the end node. So end node is going to be equal to nodes at not start at end row and end column. So now we have our start and end node defined, and what I'm going to do is initialize the distance from start and estimated distance to end for my start node, because those are values that we do indeed know. So we're going to say start node dot, and then we'll actually start with distance from start. That's going to be equal to 0, because obviously the distance from the start node to the start node is 0. And then what we'll do is calculate the F-score, and we'll say start node dot estimated distance to end is going to be equal to, and it's actually going to be equal to whatever our heuristic value is. The reason for that is that typically what we would do is we would say distance from start plus, and then whatever our heuristic is to determine what the f-score or the estimated distance to end score is. But since we know that the distance from start is 0, we can simply omit that addition and simply use whatever the heuristic is telling us. So for our heuristic, we're actually going to use a function to define this, and we're going to call this calculate Manhattan distance, and this function is going to take in a start node or some node and the end node. So now let's actually go ahead and define this function. So calculate Manhattan distance. We're going to paste that right underneath our initialized nodes. So define calculate Manhattan distance. And inside of here, we're going to take a current node and an end node. Now I'm going to start by just defining what the rows and columns of these nodes are. So I'm going to say the current row is equal to the current node dot row. I'm going to say the current call is equal to the current not current call, the current node dot call. I'm going to say the end row is equal to end node dot row, and the end call is equal to the end node dot call. Next, I'm going to return the absolute value of the subtraction of these rows and columns. So I'm going to say ABS of current row minus the end row plus the ABS of current call minus end call. All right, so now that we have calculate Manhattan distance, let's go back up into our A-star algorithm and let's define the next thing that we need, which is actually going to be a min heap. So I'm going to call my min heap nodes to visit, and this is going to be equal to a min heap that is initialized with the start node. Now you may notice that we don't have any min heap defined, but I'm actually going to pull one in, and I'll talk about how we came up with this min heap and kind of the modifications that we've made to it. So going down to the bottom of our program, I'll paste the min heap in like this, and I will state that again, you will not be expected to implement or create a min heap in a coding interview if you're going to be using it as part of your solution. This min heap class here is actually almost all taken from a question on AlgoExpert called min heap construction. I've simply copied the heap that was designed there and made some small modifications to make this work well for our problem. Again, if you were in a coding interview, simply tell the interviewer you're going to assume you have access to a min heap. These are the interfaces, or this is the interface of the min heap. Define the methods that you're going to be using inside of the min heap, and then you should be good to go. But since here we need a fully working solution, we're going to implement this min heap, and I'm going to quickly discuss some of the modifications we made to this one to make it work specifically with node objects and for this specific problem. So the main addition here is we've added a map called node positions in heap, and what this stores is the positions or the indexes of all of the nodes in the internal representation of this heap, which is really just an array. The reason for this is we need to be able to keep track of where each node is in the heap so that if we do update any of the node's values, we can automatically update it in the heap and make sure it's moved to the correct position. So the next time we try to pull from the heap, we have values in the heap in the correct place. Now, since we've added this map, there is a few other modifications that we've had to make. First, if we have a look at sift down and sift up, we can see that we are now sorting nodes by their estimated distance to end, so by their f-score. That's consistent in sift up and sift down. We also have a look at the remove function. Whenever we remove a node, we remove it from the node positions in heap as well. So you can see that right there, and we actually return the node. Moving on to insert, we can see that when we insert a node, we also insert it inside of the node positions in heap. Having a look at swap, we can see we also swap the positions in node positions in heap to make sure that matches the positions in our array after we perform this swap. We also added two new methods here, so contains node and updates. What contains node does is tell us if a node is inside of this heap, and update will simply update the position of a node. Whenever we've modified the F or G score, we can call this, and it will perform a sift up from wherever the position is in the array that this node is stored at. That again is one of the reasons we need to store the positions of all of the nodes, so that in constant time we can access and figure out where a node is, and then perform an update which will take log n time or log w times h time. So now we understand the min heap, and we can actually use it inside of our A-star algorithm function. So let's continue with the algorithm, and let's make our while loop. Let's say while not nodes to visit dot is empty. That will tell us if this nodes to visit min heap is empty or not. Then what we can do is we can pluck out the node that has the current smallest f score. So current min distance node is equal to nodes to visit dot in lowercase remove. This will remove the node and return it to us, and we'll store it in current min distance node. And then we'll check if this node is equal to the end node. So if the current min distance node is equal to the end node, then we can stop our algorithm and break. Now, if that's not the case, then what we need to do is consider all of the neighbors of the current node and update their scores accordingly. So we're going to say neighbors is equal to, and then another function that we'll define shortly, which is get neighboring nodes. And here we're going to pass in the current min distance node and the nodes. So now let's go ahead and define this function, get neighboring nodes. We'll do that underneath calculate Manhattan distance. So define get neighboring nodes. This is going to take in a node and a list of nodes. And then inside of here, we're going to start by defining a few variables. We'll say neighbors equals and then an empty list if we're talking about Python, but this could be an empty array. Then we're going to say the num rows is equal to the length of nodes. We're then going to say the num columns is equal to the len of nodes at index 0. And the reason why we know we can do that is because we know we are not going to be passed an empty array. In other words, we know we will have at least one row and one column. So we can go ahead and do that confidently. Then we can say row equals node.row, and we can say call equals node.call. And now we can start adding all of the neighbors, so checking down, up, right, and left. So if the row is less than the number of rows minus 1, then this will be our down neighbor. So we'll just do a comment there to represent that. And if that is the case, we can add that neighbor to our neighbors list. So neighbors.append, and we will simply add nodes at index row plus 1. So looking downwards, and then at index column. Next, we're going to check the up neighbor. So we're going to say if row is greater than 0, then we will say neighbors.append, and that will be nodes at row minus 1 and at index column, and this will be the neighbor up. Now we can check the right and left, starting with the right. So we'll say in lower cases, if the column is less than the number of columns minus 1, then this would be our right neighbor. And here we can add it to the neighbors list. So neighbors.append, and then nodes row column plus 1. Finally, we will check our left neighbor. So if the column is greater than 0, this again is for the left. We'll leave a comment there. Then we will say neighbors.append, and we will append the nodes at index row at column minus 1. Let's make sure our indentation is correct there. And finally, at the end of our program, we will return all of the neighbors. So that is our get neighboring nodes function. Now that that's done, we can return to our A* algorithm function and finish writing this algorithm. So we'll need to make a for loop here and loop through all of the neighbors. So we'll say for neighbor in neighbors. Then we'll say if neighbor.value equals 1, and we will continue. Now this is to check if any of the neighbors are obstacles. If their value is 1, they are an obstacle. Obviously, we cannot move into an obstacle, so we will simply continue if that is the case. Next, what we will do is we'll say tentative distance to neighbor. This is the distance that it would take us to get to the neighbor if we traveled from this current node. So tentative distance to neighbor is equal to, and then the current min distance node dot the distance from start. So imagine that this is the G-score of the current min distance node, and then adding 1 to that. So we're trying to determine the distance from the start node to the current neighbor node that we're looking at if we were to travel from the current min distance node to this node. So that is why I'm calling it the tentative distance to neighbor, because we don't know if that is actually what the distance is that we will keep and we'll update the neighbor with, but we need to check and see if it is. So we're going to first say if tentative distance to neighbor is greater than or equal to the neighbor dot distance from start, then if that is true, we can continue. What this tells us is that the neighbor already has a shorter or the same distance to get to it than what we were going to update it with. So we can go ahead and continue. We're not going to update the neighbor's values because there's no point in doing that. We either would have made it larger or made it the exact same. And in that case, there would be no change. So that checks to make sure that we are going to be updating with a good value. So now what we can say is neighbor dot came from is equal to the current min distance node. We're going to perform all of the updates here because if this was not true, then we would have passed by it. We wouldn't have continued. And well, this means the tentative distance to neighbor is less than the current g-score or the distance from start of the neighbor. So we have to update all of the values on our neighbor, including the node that we came from to get to it. So that's what we start with. Neighbor.camefrom equals current min distance node. And then we're going to say neighbor dot distance from start, and that's going to be equal to the tentative distance to neighbor. And then we are going to say neighbor dot estimated distance to end, so this is our F score, is equal to the tentative distance to neighbor, which we just updated the distance from start to, plus our heuristic. So we're going to say calculate Manhattan distance. And inside of here, we're going to pass the neighbor, this is the current node we're looking at, and the end node. So imagine we're adding the H score to the G score, and that's going to be equal to the F score as I described in the conceptual overview. So now that we have that, all we have to do is simply add our neighbors into the nodes to visit heap or update their values in the heap if they're already inside of it. So we're going to say if not nodes to visit dot contains neighbor, then what we will do is we will add the neighbor to the heap. So if it doesn't have it in already, it needs to be added. So we say nodes to visit and dot insert the neighboring node. And otherwise, if that is not the case, then that means that this node already exists inside of the heap. And since we modified its values, we need to update the heap so that it figures out the correct position with those updated values for this node. So we're going to say nodes to visit dot update. And then again, we will simply just pass the neighbor. Now I talked about these methods on the heap, but that's what they will do. They will take the node and they will either update or insert the node into the heap and then restore the heap property using it. Now at this point in time, we've actually finished our algorithm. This is the entire A* algorithm with the exception of actually building out the path and returning all of the nodes in the current shortest path. So at the end of my algorithm here, I'm going to say return and then reconstruct path like that. This will do exactly what it says. It will look at, in our case, the end node, and it will reconstruct the path if one exists to get to it. Now, the reason this will work by passing the end node is because inside of this reconstruct path function, we're going to look at all of the came from nodes starting at the end node and reconstruct the path. Now, the end node, if it was reached and we actually did break out of the loop from this condition, will have a came from on it. It will have came from a node. We will have updated the end node as it would have been one of the neighbors from our node, and it will have a came from. So if we look at that came from and we don't see one, that means that we were not able to reach the end node. But if we do see one, that means there was indeed a shortest path, and we'll have to backtrack and figure out what that path was. So now let's go and write the reconstruct path function. We'll do that right above the min heap. So we'll say define and then reconstruct path. And inside of here, we will take an end node and we will simply reconstruct the path. So the first thing I'm going to do is say if not end node dot came from. Pretty much this is checking, hey, do we have a node that we came from on the end node? If we don't, that means there was no shortest path, and well, we need to return an empty array. Next, we're going to say current node equals end node, and we're going to set up a while loop as well as a path variable, so path equals blank path, that will start reconstructing this path and traversing backwards, starting at the end node, moving to the node that it came from, and then the node that it came from that, and so on and so forth until we reach the start node or a node that doesn't have any came from on it. So now we're going to say while the current node. So this pretty much means while we actually have a node and the node is not equal to none, and we'll say path dot append, and then inside of here, we'll pass the current node dot row and the current node dot call. So we're trying to rebuild this path. We'll look at the current node, which will start as the end node. We'll add its position, starting with the row and then the column, into our path. Then after that, we'll say that the current node equals the current node dot came from. So we will have been at the end node, and then we will move to whatever node the end node came from, repeating this process and moving all the way back and kind of up the stack and up the path. Finally, we will return the reversed path. Now, the reason we're going to return the reversed path is because we start by adding the end node to our path, right? Since we're starting at the end node, the first thing that gets added inside of here is, well, the end node position. And obviously that's going to be in reverse order. We want the end node to be at the end and the start node to be at the beginning. So we simply return the reversed version of this path, and well, that will give it to us. Now, at this point in time, we've actually completed our algorithm, and I'm just going to remind us what the space and time complexity is. So having a look here, we can see that we're going to be storing one node object for every single node or position in our graph. So immediately that gives us our space complexity that we already discussed of big O of W times H. Now, same thing with the heap, we store W times H. The big O of the addition of those two is still W times H, and so our space complexity is big O of W times H. And now considering the time complexity. Now I'll go through all of the different parts of this algorithm again to show you the time complexity operations, but just note that although the time complexity of this algorithm is W times H times log of W times H, in most cases it will run in much better time than that due to the fact that we have this heuristic. So we'll oftentimes find the end node before we even consider, say, half or even 1/3 of the nodes in our graph, but there is times where we may have to consider almost all of the nodes in our graph, and that would be a worst case scenario for A star. So of course, when we do our time complexity analysis, we have to consider it in the worst time, but it may be worth bringing up in your interview that generally A star will run much faster than the given worst case time complexity. So the first thing that we have to look at is the while loop. We know that this is going to take W times H time to run at most, because we know we could have at max W times H nodes inside of this nodes to visit min heap. Then we have to remove the minimum element from this heap. This is going to take a log of W times H time. Then this is a constant time operation. So is this, and inside of our for loop, at the very bottom, the only non-constant time operations are these, which will again take a log of W times H time to run. So that gives us a total time complexity of big O of W times H times the log of W times H time. And then again, that gives us a space complexity of big O of W times H space. And with that, we'll conclude this video. So I hope that this video was helpful to you and that you now understand the A star pathfinding algorithm. With that said, I look forward to seeing you again in another AlgoExpert video.